Welcome to this video. My name is Mark Scythian. The date today is August 7th, 2024. So if we take the previous video, the horizontal water flow velocity and range video, and we modify the duct into a Hydrojet application, we can compute the application's performance metrics using similar hydrodynamic and thermodynamic applications and fundamentals. So assume we have a hydrojet duct and it's connected to a gas turbine engine, a turboshaft engine with 1535 shaft horsepower, and it drives a hydro pump, which may be a centrifugal, axial, or mixed flow application capable of drawing in water from an underwater environment through its intake up through the pump. We have a pump efficiency of 90%, a hydraulic pump efficiency, that is. And so eventually the water will flow through this duct, decavitate, and then become hydraulic or incompressible, but it's going to flow through the duct with the same taper ratio of 1 to 0.33. So we have a continuity of flow due to the incompressibility of the liquid, in this case water, right? So from that point on, we can reduce the amount of complexities to predict the performance metrics of such a hydro thrust or jet application. So, of course, we're going to just use the taper ratio to find out what the jet nozzle diameter is. So that's just 0.8 feet intake diameter, tapering down to 0.264 feet diameter jet nozzle. So we can rename this as Hydrojet Application. So this will be the hydro thruster mounted on a boat, and the correlating performance analysis. So we start with the 1535 shaft horsepower multiplied times 0.9. So there's going to be a hydraulic power of 1381.5 horsepower. And then the 700 gallon per minute flow rate of the hydro pump divided by 60 seconds for gallons per second times 8.3 pounds per 1 US gallon. So we have a mass flow rate of 96.8 pounds per second. So we know there is 550 foot-pounds per second to a horsepower times 1381.5. So this is 759,825 foot-pounds per second of mechanical power in the form of hydraulic, or we'll call it hydrodynamic power of the water acceleration. So if we were to simply take the 759,825,000 foot-pounds per second and divide it into the mass flow of 96.8 and then multiply it times the pressure ratio. So instead of going by memory, we'll conduct another calculation to see if that pressure ratio is right. So if we simply just divide the taper duct intake cross-sectional area into the jet nozzle cross-sectional area, we can calculate the pressure ratio. So it's actually 9.2 to 1. So instead of having to measure the duct length and go through all of these details, we have a hydraulic effect, so the displacement at the discharge of the pump is equal to the displacement through the intake, and we'll just assume that this is a equal diameter to the intake. It's not drawn to scale, of course, so we don't have to concern ourselves with the details of the flow. As long as the duct structures are decapitated of air, then we could just omit the complexities of the work divided by time, or the force times distance divided by time, to foot-pounds per second for the mechanical or hydropower in this case. So the only thing is that we're going to lose that power as we overcome the pressure ratio. So this then scales down to an output discharge velocity of 853.2 feet per second of the water mass flow out of the jet nozzle. So that's based on the conservation of energy. We can't create or destroy energy. So after quantifying the ratios and the distributions across the hydraulic lock and flow, we compute approximately 850 feet per second of hydrojet velocity. So that would be the component V2. Next, we take the 96.8 and we multiply it times 96.8 pounds per second. We multiply it times the final velocity of 853.2 feet per second, then divided into gravitational acceleration on Earth, 32.2 feet per second squared. And this computes to a static thrust of 2,565 pounds thrust. So that's static thrust, F sub G. Then the relationship between pressure and velocity is 1/2 rho V squared. So rho is the density of the fluid, in this case water. So using the metric system, that's 1,000 kilograms per cubic meter times 0.5, then times the 853.2, or just say 853.2 converted to meters per second divided into 3.28, then that quantity squared. So we compute actually 33.8 megapascals. When divided into 6894.76, we get 4907 pounds per square inch gauge pressure. So if we were to divide that value into the pressure ratio, then the inlet of the duct pressure becomes 533 pounds per square inch gauge pressure. So call that the entry. And then we have our jet nozzle. So that's the pressure differential, just to get an idea of the overall relationships on the pressure differential. So we have approximately, say, 2,600 pounds of thrust, between 25 and 2,600 pounds of thrust, 9.2 to 1 pressure ratio, 853 feet per second jet velocity, 96.8 pounds per second mass water flow, 4907 pounds per square inch gauge pressure at the jet nozzle, and at the inlet of the duct 533 psi gauge. And that is dynamic pressures, duct entry pressure to jet nozzle discharge. Now the last point is the fuel consumption. So we may see more hydrojet boats, except for the expense on using a gas turbine for practicality, and then the very costly fuel consumption. which will be proven here. So assume that you're using the turboshaft with a typical shaft or equivalent shaft horsepower, like from a Honeywell application. So right there, using kerosene jet fuel, we have an energy density of 18,730 BTUs per pound. And then we have a fuel density of 6.75 pounds per US gallon. And that is like JP4, JP5, JP8. It's approximately the energy density and fuel density values. And then the brake thermal efficiency of just about any gas turbine engine is 40%, whereas gasoline it's about 30%. So we can multiply the shaft horsepower output times 746 to compute the mechanical watts. We know 1 BTU per second is also equal to 1056 watts. So that's a typo there, 1056 watts. So we take the mechanical wattage, 1,145,110 watts, and divide it into 1056 watts, the number of watts to 1 BTU per second. And we compute 1084.4 BTUs per second. But then we have to account for the actual fuel consumption, which is then rescaled to the thermal efficiency and its reciprocal. So 1 divided into 0.4. One divided into 0.4 is 2.5 times more fuel consumption than what we get at the output drive for useful or usable mechanical power or brake horsepower. So this thing comes to 2711 BTUs per second. We divide that into the energy density of the kerosene jet fuel, 18,730 BTUs per pound. This comes to 0.144 pounds per second kerosene jet fuel consumption. And then if we find the inverse or the reciprocal of that value, every 6.9 seconds, 1 pound of kerosene jet fuel will be consumed. So if we want to figure out what the gallons per minute fuel consumption is, we first could divide 60 seconds into 6.9, so that's 8.7 pounds per minute kerosene jet fuel consumption, and then divide that value into 6.75. So this will burn 1.3 gallons per minute fuel consumption. So it's not fuel efficient at all, and it would be very expensive and be more like a recreational activity unless people have deep pockets to commercially invest in a hydrojet application. So this tells us a lot if we were to scale this down and make it much smaller using perhaps a diesel power plant or even a high-end gasoline two-stroke. It still would correlate to a proportionally not fuel efficient piece of equipment, because we see some people trying to build hydrojet applications and everything goes smooth and they have a lot of fun with it, but they run out of fuel very quickly. So that's one of the reasons we don't really see hydrojet thrusters other than underwater or inboards, because you don't really have to worry too much about accelerating the water from one medium into another, where you can keep the medium within itself and then just take advantage of thruster ducts, and so you reach much more efficiency, overall efficiency. other schemes such as running really large impellers, rotating at low RPM and high torque. And so there's a lot of gas turbine hydro thrusters that are on the cruise liners, the ones built there in Scandinavia. And so those are pretty efficient, but based on the cost and the size and the efficiency. So it's actually a really sweet engineering setup for business in that industry. But that's one of the drawbacks. Even if you were to use something really tiny, you'd get all this thrust even from a two-stroke high performance application, but it definitely wouldn't be very cost effective on the fuel efficiency end. And that's when perhaps it becomes a cost prohibitive activity, or it's really not worth the investment. So this video was made for those that may be building hydrojets. And of course there are other issues about having a safe operating zone or space / range for one of these devices. But in the long run, the major hurdle about, let's say, funding a hydrojet is the poor fuel economy. So thank you for watching this video and have a great day.